which was recently completed by, if you want, the proof of the existence of smooth steep functions, so that we really could take this inf over a subset, if you want, an appropriate subset of our algebra of smooth functions on the manifold. And the formula reads like this. And so you see that everything, in a sense, gets flipped in the Lorentzian case, and the usual soup of Kahn's formula here becomes an infimum. Okay, and of course, if you want this dichotomy, between I mean P2 in the future of P1 and the converse is encoded, okay, in this function, which is denoted like with these square brackets and the plus here, which if you want, cuts to zero the distance in case the causal relation between the points is not the causal relation of these points is not the usual one. I mean, the one is not in the future of the other. Okay.
Luca, one point. This infimum is coming here. It has nothing to do with the fact that you are using one kind of the signature. It has nothing to do with the signature you are using. If you flip the signature.
No. If you want, it's I mean, if you want, it's just. No, it has nothing to do with, okay, this, I mean, at least if you say the signature, in what sense? Of the space, of the fact that it is Lorentzian, yes, of course. This, I mean, since it is Lorentzian, then we have an inf instead of...
I'm asking if you use mostly positive or mostly negative signature, it will not change.
No. Positive or negative?
Mostly positive signature, plus, minus.
No, okay, excuse me. Here, perhaps I should have said it from the outset, okay? Here we are speaking about, now this, I just mentioned the general pseudo-Riemannian case, just to speak about that converse result from Franco and Eckstein. No, but now here we restrict to Lorentzian signature and taken with let's say the physicist convention, okay, so that the metric has a minus at the time for the time component and a plus for the space component, so that of course if you change the sign of the metric, then you change, if you want, you change the sign of everything, if you want. But okay. Now the important point here, is that okay, this is a completely satisfactory result, of course, but if we are interested in the geometry of the manifold, meaning, as you see, this is a distance between points, and from the point of view of non-commutative geometry, this means a distance between pure states. Okay, but in order to pass to non-commutative geometry, we need to understand what happens for general states. Okay, so on the one side, in the commutative case, we might wonder, for example, an important point. Okay, these steep functions, okay, have a gradient which is strictly negative, or if you want, past directed, and it is easy to understand that they cannot be bounded. Okay, this is the point. And so, in a sense, okay, this object here is okay, associated to the algebra, but in the end it is a set which is made out of unbounded functions, smooth unbounded functions on the manifold. But of course, points have, I mean, pure states in this case. Points, are measured with compact support, and so we don't need. I mean, we don't care, about what these functions do at infinity. We don't need to care. Of course, this will be the case also for compactly supported measures. Yes, but for example, as we know, we will see explicitly in the case, even in the case of the Moyal plane, certainly not all pure states will be associated to compactly supported measure. So we have to generalize this formula, and also considering this general case is very important because it makes clear that many problems that are there with this Lorentzian formula are already there in the non-commutative case, are already there in the commutative setting. Okay, and okay, I just write down, this slight generalization, okay, meaning there is okay, and we need to ensure that for general states, even evaluating the state on perhaps a t, there should be a t here, the state on these unbounded operators makes sense. This is not clear. No? We are left with this problem of extending states on the states on the sister algebra, so states which are defined on bounded elements, to these unbounded elements, to these, in this case, steep functions. Okay, so in the commutative case, in principle, this makes this is not there is no problem in the commutative case. Why? Because we have the Ritz-Markov theorem at hand. No, we really know that states are measures. Okay, so that the set in which we take this inf is a set of smooth functions, so that we can certainly and always make sense of their integral. Maybe it will be divergent, but it will certainly always make sense. And so when we consider this formula, we only have to, if you want, we only have to take care of the fact that the corresponding the functions here actually are really, if you want, integrable, something which we do in this natural way, which is inspired again from ongoing work of again Eckstein, but also other authors on the connection of, on, if you want, Lorentzian optimal transport. This is actually where I got. Okay, perhaps the simple idea not to restrict to this case. Of course, this is what motivates this choice. If you like, you use different criteria, not to ensure the finiteness of the states applied, or the fact that the elements here are really in the domain of the state. Okay, and in case we have to take into account the possibility then, but this is a phenomenon which is well known even from the Euclidean case, no? That okay, the distance then between the two states may be infinite, and okay, here we have this difference. We define simply the distance to be plus infinity, since here we have an inf. If the set in which we take the inf is empty, then we set it equal to plus infinity. And this provides, in this way we have a distance formula which is valid for arbitrary states on our commutative algebra. Okay, now I present what is the again, if you want, Franco-Eckstein axiomatization of a Lorentzian spectral triple. Now I said that okay, my aim was not generality, but really the spirit of these axioms actually is generality, if you want, in the sense that they include all known examples of and definitions of Lorentzian spectral triples. For example, we have Sitarz here who gives a slightly different and more articulated axiomatization, but yet. So we extract the elements which to pass to the non-commutative case. And so first, okay, of course, a Hilbert space, a non-unital, because we are speaking about, if you want, a globally hyperbolic spacetime, namely we are speaking about non-compact geometries, with a faithful star representation, a preferred unitization. We will see in a moment that perhaps, that this is a somewhat delicate point. Everything here must be, they all must be pre-sister algebras as usual, and so, and also, okay, we have some compatibility conditions between A tilde of A. And in any case, A tilde is a unitization, an appropriate unitization of A. And you see, okay, we extract, the properties of, here are the properties of the Dirac operator. And here you see, okay, the Lorentzian nature of our triple, okay, forces us, in a sense, to impose second order conditions. For example, there have been attempts by Renyi to only to axiomatize the spectral triple only imposing condition, first order in this sense conditions, but even if they work, they fail then to they fail in the commutative case. So it seems that we really need, if you want, to impose conditions on this square, and by this, of course, I mean the Hilbert space adjoint. Okay, this is then the analog of the compactness condition. Remember that we are dealing with non-compact geometries. this is our Krein symmetry, since we had the talk of theta's before, not to be confused with the real structure on the spectral, on a spectral triple. Here we see, and this is actually a very natural condition, actually, no? That the elements of even the unitization are taken to commute with our Krein operator. And I regard this as a natural condition in the sense that, I mean, the signature, I mean, the Lorentzian nature of the geometry comes from, of course, comes from the metric. And the metric is not, I mean, is an extra to the topology of the space which should be encoded in the sister algebra. No? Okay, and okay, and this is this expresses actually the fact that the operator D, or ID, if you want, is has to be taken has to be taken Krein self-adjoint. And here, okay, there is a parity operator. We have to make some assumptions on the relation between the Krein symmetry and the parity operator. And okay, actually, this is apparently, let's say, a useless and obvious fact, but okay, even if I will not be explicit, I will say that, I mean, this is the very reason why we will see later, I mean, the set in general, we can prove that the set of steep operators will be contained in the set of causal operators. Okay. And as a final condition, really defining, the, if you want, the globally, this is the globally hyperbolic nature, if you want, of our space-time, we ask for the existence of this distinguished coordinate operator, okay, which should be seen. Oh, okay. Then I'm completely okay. Then okay. And I mean, what was asked for these operators was just this condition, which expresses the fact that the coordinate T should be somewhat linked to the algebra. But okay. Finally, a causal structure was introduced by Franco and Eckstein, mimicking, as I told you, the equivalence I was speaking before, between causal functions and that the positivity condition of this thing here is expressed in this way, and the causal order, the spatial order, there should be a 1, of course, here, is just introduced by means of this causal cone, namely all the elements that satisfy this condition. Okay.
Sorry, Luca.
Yes.
The D should be a T, or?
The
first equation, the D is a T, or?
The D?
In the first displayed equation.
T, yes, yes. So, no.
The commutative is between D and T.
D and no, all elements of let's say your unitization, here there should be a T, all elements of your unitization such that they satisfy this condition, okay? And if I mean this completeness property, if you want, I mean if this span really gives you all the algebra, then you say that this C, this set, this subset of A tilde is, you call it a causal cone. But now, okay, now I have to go a little bit fast. But okay, my main message here is that to give a general formulation of the distance, okay, we need to kind of strengthen the conditions imposed on these time operators, which also, I mean, look, I mean, this condition here really is well defined, if you want, only inside the representation on which the Dirac lives. It is not sufficient to say that the time operator is abstractly linked, this time coordinate, if you want, is abstractly linked to the algebra, okay? And this is why, this is, if you want, the epistemological reason also to consider the well-known, now I go a little bit faster, excuse me, of the notion of unbounded multipliers, namely, or if you want, unbounded elements affiliated to the sister algebra. This notion was introduced by Voronovich. And, but the essential property of these objects, being intrinsically linked to the sister algebra, is the fact that any representation of a sister algebra extends to these unbounded elements. And this will be the key ingredient allowing us to extend the states to these unbounded elements. Now, this is the point, okay? The trick, if you want, to be used to extend this formula to the non-commutative case is just this one. No? We, using unbounded multipliers, no, we can, yeah, we just can make this extension, and this is okay. This notion, okay, I call them regular Lorentzian spectral triples, namely Lorentzian spectral triples in the sense of, if you want, Franco and Eckstein, but for which these these causal operators are taken to be affiliated to the sister algebra. And okay, forget this A tilde affiliated notion, this is not important. But and we can consider then the set of affiliated causal operators. And here, just as a side remark, this almost allows us to exclude compact geometries, okay? Something which could not be done with the weaker condition imposed by Franco and Eckstein, okay? Okay, this will be the analog of the causal cone, no? If you want. We take unbounded elements affiliated to the sister algebra which satisfy the causality, the causal cone conditions before. And I was speaking before. And if this, if you want, is the trivial trick to extend the states, to always extend the states to these unbounded multipliers. Namely, since any representation of the algebra extends to the unbounded multipliers, we simply consider the GNS representation corresponding to a state, and we say that the unbounded element is in the domain of the state if essentially the GNS vector is in the domain of the operator, of the modulus of the operator, of the square of the square of the operator you choose. I choose this thing in analogy with the commutative case, and this allows you to define, to always define this extension. And okay, this is just the same definition of Franco and Eckstein of a causal order, but with the causal cone extended to these unbounded elements. Okay, of course, the causal cone, the bounded causal cone of Frank-Wedeckstein will be inside ours, so that, I mean, the relation is very simple. Okay, and the distance formula is just here. So you see, we only need to impose that the unbounded elements then is in the domain, now perfectly well defined. Now, okay, this notion is perfectly well defined on the two states, and we just need to write down the obvious generalization. And so this gives us a general formula for the distance in Lorentzian non-commutative geometry. Okay, now it's over. Ah, okay. Okay, now, okay, I don't need to explain this. This is really the standard material on, this is the two-dimensional Moyal plane. So the really extra well-known case. Here we have the Krein operator on our Hilbert space. This will be the parity. The Dirac is, of course, the natural one. And with all this, we see here the. Okay, we pass, it's useful to pass to light cone coordinates, and in this way, this condition looks like this, so that an element of our algebra will be in the causal cone if these two conditions are satisfied. This is the explicit form. So you see, in a sense, that, okay. This is standard material. Okay, we will need coordinate operators. Of course, they are affiliated to the sister algebra, which in this case is the compact operators. This is very easy because the elements affiliated in the sense of Voronovics to the compact operators actually are all closed operators on a Hilbert space. So in this case, everything is trivial. We have an action of translations, of course, on this Moyal plane. Everything goes as expected, and here I see which is the class to which I now restrict the attention. The class which will be considered in evaluating causal relations and the distance. Okay, but here we don't look for a maximal generality. This could easily, of course, be weakened, but it doesn't matter. Okay, this is, we are over. This is the first result. Okay, pick this smooth state. Okay, consider it's translated, of course, by a time-like vector. Okay, consider it's translated. Okay, and then as it is to be expected, the result is simply that they are causally related if and only if the translation is time-like. So we have the expected result. The proof is almost all over there. It's just the definition in the end. The proof is almost only the definition. And then here we have the second and final result, which again is as it was to be expected. This is the Minkowski distance in light cone coordinates. And okay, and we see that we just write explicitly the condition here to be steep, which takes this form. So we see that it asks that these two, the vector psi d plus f not psi, and one component, psi d minus f psi, the other component, is time-like. This is equivalent to asking this, and this is important because, okay, we just use the fundamental theorem of calculus. We apply the reverse Cauchy-Schwarz inequality because here k, the translation, is assumed to be time-like. The vectors, these averages, if you want, are time-like vectors, so we can use the Cauchy-Schwarz, reverse Cauchy-Schwarz inequality and attain this inequality, which is always true then. And okay, and now since we are considering a bounded operators, okay, we just consider as optimal elements this particular linear combination, which happens to be affiliated to the sister algebra, and so it is inside. It is inside the set in which we take the inf, and then this is rather obvious from this. The fact that the inf is attained is rather obvious from this formula, and okay, and we are done. Okay, so this is a short biography, and okay, excuse me for the. Okay.
Thank you very much.